I think I'm live now. Can anyone confirm if audio, video, etc. everything looks fine? Hello, hello. Can anyone confirm if I'm audible or not? Hello. Okay, thanks, Gyanvi. Okay, I will wait for a few more minutes. Meanwhile, people in the chat, like, how many problems were you guys able to solve? Like, that will give me some rough estimate on which problems to focus most on and which we can probably move faster. Like, I ended up solving all the problems, so I will be discussing all of this. So, like, how many problems were you guys able to solve today? Okay. Snack Packer 1 said I solved only 2. I solved only A. Okay. Okay, 6. Good one. Okay, 6, 3. Okay, makes sense. Hello. F was really tricky. Like, I feel G was much more trickier than the F one. Like, F is becomes quite straightforward if you know what Lucas theorem is. So, like, I will probably discuss on this one, but yeah, like, those who knows Lucas theorem, F becomes a bit more easier. Okay, solve 3, 2, and I think I will get started now. Okay, so like new world, new me, new array. Natsume Akito, let's call it NA, has just woken up in a new world and immediately received his first verse. The system provided him with an array of n zeros and an integer k and an integer p. In one operation, Akito chooses two integers I and x, such that I is between 1 to n and x is between minus p to p, and performs the assignment ai equal to x. Akito is still not fully accustomed to controlling his new body, so help him calculate minimum number of operations required to make sum of all elements in the array equal to k, or tell him that it's impossible. So let's look at what the problem statement says. We have an array A of length n. Everything is 0 initially. Let's, like, we can replace any number with any value between minus p to p. So for example, let's say we have replaced this with 3, this with -1, this with -2, this with 10. Now the sum is 10, and number of operations we have made here is 4. So it asks us to find the minimum number of operations we want, such that we can get sum equal to k. So the idea is, like, we can first ignore the sign of k here. Sign of k. So for example, number of operations we need to have some minus 10 is same as some 10, because like every number can be between minus p to p. So we can find minimum number of operations to get some 10 and then multiply everything by minus 1. So we will get minus 10 as a sum there. Now the question is, like, if we have n elements, then the sum we can have is between minus np to np. So if the required sum is outside this window, print minus 1. It's impossible. Otherwise, we have to just print required sum divided by p, and we will have to take c here. Or alternatively, we can just run a for loop over here and try to find like how many operations would be enough. Because like if we modify L elements, then the sum we can get is L into P and L into P. So we can just check what is the minimum L required over here, and that's all we need. The solution I ended up implementing was read nkp. Ignore the sign of k by taking absolute value of k. Then now find the seal of k divided by p. Like this is another way to find the seal. Then if m is number of operations we need is more than number of elements we have, print minus 1. Otherwise, print the operations we need. And this was it. Any questions, anyone, before we jump on to the next problem? Okay. Any questions, anyone, on A before we move on to B? Okay, I'm not sure why I'm getting echo here. Like that's not supposed to be how it is. Okay, like are there any echoes, people, or like are there any questions on A? Like you can just say yes, no, yeah. Okay, good. Then in that case, I think I will move to problem B. After completing the first quest, Akito left the starting cave. After a while, he stumbled upon a goblin village. Since Akito has nowhere to live, he wanted to find out the price of housing. It is well known that goblins write numbers as a string of hyphen and underscore, and the value represented by a string is number of distinct subsequences of string s that are equal to hyphen underscore hyphen. This is very similar to goblin faces. For example, string s, this represents the number 6 because there are 6 subsequences over here. Like for example, if we take first character, second character, third character, we will get a goblin face. If we take third character, fifth character, sixth character, we will again get a goblin face here, and similarly so on. Initially, the goblin wrote a random sequence S in response to Akito's question, but then they realized that they wanted to take as much gold as possible from the tavern. To do this, they ask you to rearrange characters in S so that the value of number represented by string S is maximized. So one more good problem here can be given string S, find the goblin number here. Like that's what I initially coded. But here the problem is asking us, you are given some set of characters. You can rearrange them in however way you want. Now you have to find out what is the maximum goblin number we can have over here. So that's our problem statement. So like let's let's first focus on like how does a goblin number impacts. What we need is count of dash underscore dash. Let's first ignore all the underscores and try to write the string like this. Let's say these are all the dashes we have, and now we have to put some underscores in between. Let's say if we put an underscore here, the number of dashes you will be able to form is number of hyphens on the left side and number of hyphens on the right side. So if you put something here, you will get 1 into 1, 2, 3, 4, 5. 1 into 5 goblin number. But similarly, if you put underscore here, you will get 2 number of hyphens on the left side and number of hyphens on the right side, 2 into 4. If you put underscore here, the number of goblins you will get is 3 hyphens from the left and 3 hyphens from the right, and so on. And similarly, like for example, let's say if we have T hyphens and 1 underscore, then like if we put underscore after first P hyphens, then the number of goblin would be equal to P into T minus P. Number of goblins on the left and number of goblins on the right. And we know that the maximum value of this expression happens when like P is equal to T by 2. Like you can try to figure it out using binomial identity, parabola maximization, differentiation, or whatnot, but this is a bit known result. And now what we know is if we have 1 underscore and T hyphens, then the best way to get maximum number of goblins is put it in the between at the middlemost position, half of the characters on one side and remaining half on the other side. But for example, if T is odd, you can just put 1 extra character on any side. And the idea is like for each underscore, you can try to independently find how many variables are there. So if we have, let's say y underscores, then the number of maximum values we can get would be this expression multiplied by y. Because wherever we place underscore doesn't really matter because they don't impact each other. Essentially, this is the idea. So like the answer turns out to be P equal to T divided by 2, and then print P into T minus P into Y, where T is the number of hyphens and Y is number of underscores. Any questions, anyone? So H plus 1 by 2, H by 2 into V, essentially that's what it turns out to be. Any questions, anyone? On like, yes, long was required here. Like the numbers are up to 2v5. So the maximum value you can get is up to 10 to the power 15 or something. So you will have to use long. Yes, I will jump onto the code now. Like the code is C1 is the number of hyphens, C2 is the number of characters. Then for each underscore we have, this is the number of goblins we can get. Put half of the hyphens on one side and remaining ones on the other side. And because underscores are independent, just multiply answer by number of underscores you have and print the answer here. So this is the idea. Like LLI is short for long int. So this was the idea. Any questions, anyone on problem B before we jump to problem C? Like when do we use, like the key idea is integer supports number up to, let's say, minus 2 into 10 to the power 9 to 2 into 10 to the power 9. While long int supports numbers up to 4 into 10 to the power 18 to 4 into 10 to the power 18. And in this case, like the answer, for example, this is the formula for the answer. Let's say if T is equal to 10 to the power 5, P would be equal to 5 into 10 to the power 4, and this answer would turn out to be 5 So let's say y is equal to 10 to the power 5, p is equal to 10 to the power 5. Because we know that the total length of the string can be up to 2 into 10 to the power 5. So the answer you will get would be 5 with 4 zeros and 5 with 4 zeros and then 10 to the power 5, which is essentially equal to 25 into 10, 5, 9, 10 to the power 13. And this is much more than what an integer can support here. And that's why you have to use long long. Or yeah, like one key rule can be you can just use always long int and that's fine. As long as you use 34-bit for the solution. 64-bit for the solution. Like just use programming languages 64-bit and just use long. That should be fine. So this was problem B. Any questions, anyone, before we jump on to problem C? Okay, I will jump on to problem C now. Akito still has nowhere to live and the price for a small room is everywhere. For this reason, Akito decided to get a job at the bank as a key creator for storage. In this magical world, everything is different. For example, the key for the storage with code n, x is an array of length n, such that or of all the numbers is x and the max is maximized here. Akito diligently performed his job for several hours, but suddenly he got an headache. Substitute for him for an hour for a given n and x, create the key for the storage code n, x. So we are given in n and x, we have to create an array of length n, such that if we take or of everything, we get x, and if we take max of everything, we get the maximum possible value here. So one thing you can notice is like max means the smallest number that is not present in the array. So our best bet would be we start filling in numbers from 0, 1, 2, 3, 4, everything until let's say n minus 2. Let's say smallest number not present in that. So our best bet is if you want to make it maximum. Like for example, 0, 1, 2, like let's try to put smallest number as possible, 3, 4, 5, 6. So and there would be some number which we cannot use either due to or we just ran out of space and only one blank space is remaining. Then we can put the remaining number here so that we can get the required or here. And essentially this is the idea for this problem. Like keep filling numbers from I equal to 1 to n. Basically fill n minus 1 numbers. Or I can put it more like this. Try to fill it up to n minus 1. So you have filled in all the numbers. Then look at or. If it is equal to x, we are good. Because this is the maximum max we can get. And like while filling in the numbers, only take subset of I to begin with. And whenever like I is not subset of x, break and put 0 everywhere. And essentially this is the idea we have for this problem. The idea is since you want maximum x, you want to pick the smallest number, all of the smallest number which you can. So you start with 0, 1, 2 and so on. Whenever you cannot add number because that will lead problems here, you see or of all the numbers means all the numbers should also be the subset of x. Then you immediately do a break there and put all the remaining numbers as 0. But if you end up filling all the numbers from 0 to n minus 1, you just check if or of all the numbers is equal to x or not. If not, then you can remove n minus 1 and put that with the required value we have. So essentially that's the idea. I think I will code on this one. For LLI I equal to 0, I less than 1, I plus plus. If I is not a subset of X, break here. Otherwise, A dot pushback, just put I at the end. Now I take what is the OR of all the numbers I have filled so far. And like I can just fill in the remaining place with all the numbers from 0 to 1. Like I just put in current all as whatever numbers I need. Let's say this is required all. If required or is not equal to current or, just remove the last number. And then add A dot popback. And this is how we will solve. Yes, I will post this problem on YouTube and all the solutions I am explaining would be. Like the idea is, like max means smallest number that is not present in the array. One second, where is my time? Like first thing we need to understand what is OR here and what is max here. Max means the smallest number which is not present in the array. So if we want this value to be as much as possible, we will have to put in all the numbers that are not present right now. So we will start with 0, 1, 2, 3, whatever we go. And then we have a constraint that OR of all the numbers should be X. It also means if OR of all the numbers is X, then all the numbers should also be subset of X. Means all AI are subset of X. Like this is an introductory problem. Like we have three things here. We have maximum value of MEX. And then we also have OR here. Like I think I can take one of the examples if you tell me which sample to pick. Okay, let's take this example 7 7. No, like 7 is a bad example. Let's take n equal to 10, n equal to 10, and x equal to 11. So what I will do is I will first put 0 here. So now I have to put in 10 numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. First I put 0 here. 0, like because if I don't take 0, then the smallest number that is not present in the array would be 0. So I am good here. Now I take next number, which is 1. 1 is also a subset of 11, so that is fine. Then I will put 2 as well because that is also not here. Then I will put 3 here. But when I try to put 4 here, that will be a problem. Because like no matter what, 4 and whatever other numbers I make, 4 and or of some more numbers, whatever numbers I have, can never be equal to 11. This is because if you look at the binary representation of 11, it looks more like this 1 0 1, and 4 looks more like this 0 1 0 0. And if you take OR of any number, and what are numbers we have 0 1 0 0, and it does not matter what we have here, we will always have this bit as 1 here. While for 11 we want 1 0 1 1. So this can never happen over here. And that is what I mean by subset. Like I will place numbers in such a way that I can still have OR of all the numbers as 11. Like subset, I think, is like you will have to look at the binary representation and ensure that all the ones where you are getting also appears as 1 from the other number. Like for example, if I want OR to be 11, in binary it looks like this: 1 0 1 1. So only numbers, like, so all the numbers should have 0 here, and here they can have a wildcard, whatever they want. So this was the idea. So now my problem ends here. I can just put everything else as 0 0 0, and we are good. Because we cannot add 4 here, so it doesn't matter what all we add. Like, one more thing I am doing at last is, first I create an array like this, then I take if OR of every number is equal to given OR or not. If not, then just put the required OR here, which is 11. So essentially this is the idea I have for this problem. So now coming back to 7 and 7 example. Like I will first put 0. 0 is a subset of 7. 1 is also a subset of 1. 2 is also a subset of 1. 3 is also a subset of 1. 4 is also a subset of 1. 5 is also a subset of 1. 6 is also a subset of 1. So now I have added all the numbers which I can. And if I check OR of every number here, which will come out to be 7 as well. So that's why this example is valid. Let's say it was, instead of n equal to 7 and x equal to 15. In this case, OR would be 7. So I will just replace this value with 15. And essentially that's the answer I have. So idea is immediately stop whenever you cannot add the smallest number you still have. So essentially this is the idea. I don't need this here. So this is the solution we have for problem C. Any questions, anyone on problem C before we jump to problem B? Check. I don't know my typing speed because I make mistakes when I check on English essays. And like, I don't know, like, let me see where is the problem. Okay, this should be required of. Okay, a dot popback, a dot pushback. So essentially, this is the solution for this problem. Any questions, anyone? Otherwise, we will move on to the next problem. Yes, current or not equal to required or does matches bitwise because it checks numbers, right? Like at the end of the day, these are just integers written over here, and taking or creates or bitwise. Like this should be we are checking it as a subset. This can be one way to check it. Another way to check here would be like, if I take OR of 1 with required, this should be equal to required OR. That can be another way to check the same thing. This also works. Like this essentially checks whenever we have, wherever we have 1 should also be the place wherever we have I. Okay, why are we putting the x in the end of some zeros? Yes, like the idea is we can fill in zeros everywhere we want. Oh wait, no. This should be not equal to. So this was problem C. Any questions, anyone? I will otherwise jump out to problem D. Well, like the problem is we cannot continue there. Like the numbers are up to 2 into 10 to the power 30. So let's say you have 2 into 10 to the power 30. You cannot just go from 0 to 2 to the power 10 to the power 30 to print the first number. That's where I just break, and taking or with 0 does not changes the overall or of the problem here. For result, the exam is easy, but I couldn't handle it. Akito got tired of being simple locksmith at the bank, so he decided to enroll in Magical Academy and become the best wizard in the world. However, to enroll, he needed to solve a single problem on the exam, which the ambitious hero could not manage. Which the ambitious hero could not manage. In the problem, you are given an array A of length n. He needed to minimize the number of inversions in the array after applying the spell exactly once. The spell was simple. To apply it, Akito can choose two integers, two numbers L and R, and perform a cyclic shift of subarray from L to R, one position to the left. More formally, Akito selects subarray L and R and modifies the array as follows. The original array is A1 to AL, then AL up to AR, and then AR up to AN. He obtains the array A1 to AL minus 1, then AL plus 1 to AR, and then AL and AR plus 1 to AN. Akito is eager to start his studies, but he hasn't passed the exam. Help him enroll and solve the problem. So the question is like, if you look at this array, like let's get away with this cyclic shift. It's like picking up one number and putting it at some another place after it. And it asks us to find like what is the maximum number of inversions we can get over here. Like A1, A2 up to AL up to AR, then AR plus 1 up to AN. This is the original array. And now what we are essentially doing is picking it this number and putting it after here. So like the idea is like if you look at all the pairs which are already here, like the inversions can change only if AL is involved. Like if you look at the relative position, like of AI, where I is between 1 to L, has changed with AL. And essentially that's the only change if you see, right? Like because for all the numbers, let's say A1 and something here, A1 will still remain before the numbers here. Similarly, if you look at two numbers here, their order is still same. So if they were invert before, then they will invert now as well. One more thing is like what is inversion to begin with? Like for example, you can find this example here. 4-1 is one inversion. Like inversion is a case when for a pair, like the larger number appears before the smaller number. And if you look at any numbers here, there also nothing is changing here. And can I say, let's say for example, if AI is greater than AL, then the earlier the array was like this: AL, then some AI, and then something like this. It was not an inversion. But now once I move it here, it will now become, after operation, it becomes inversion. Yes, like I will definitely upload it on YouTube. And similarly, the other way around. If AI was less than AL, earlier it was like this: AL, then some AI, and then these numbers. And this number was larger than this, so it was an inversion before. And after operations, it's not an inversion. And essentially, that's the idea for this problem. What we can do is, like, we can just maintain the difference of number of inversions we can get from current array and the original array, and then try out all the L2R pairs here. And we can pick the one which decreases the inversion the most. Some example here, like let's pick this example only: 31415. Let's say we move this 3 to here, 1 to here. So earlier, like, and now the new array becomes 3141 34115. This 1 and 4 was not an inversion here, but it's an inversion now. And the vice versa. Let's say we put this 1 with 0 here. This is also 0. And earlier this 1 and 0 was an inversion. Now it's no longer an inversion. And essentially, this is the idea for this problem. Instead of changing the array and trying to find all the inversions at once, we just maintain, like, what is the extra delta we can get for the inversion if we do an operation between these L2R. And essentially, this is the solution. So for example, like, I start from one particular L and I go for all the R's. If the new array element I'm extending is less than current element, then earlier it was an inversion and it's no longer an inversion now. But if the new element I'm extending was more than AL, then I am moving it before AR. So I am increasing the number of inversions here. So I maintain this counter and I just take minimum with whatever best value I have got so far. 04 also works. What do you mean by 04? Which example you want? And yeah, like, there can be multiple boundaries which can give us the best answer. And this was essentially the solution we had for this problem. And any questions, anyone? And like, if you don't want, like, if this tuple looks a bit easy, best change, answer L equal to 0. This is when we don't do anything here. Current change, if best change is more than current change, we can just put in offset by 1 because I'm using zero base induction. And this also works. So this was essentially the solution D. Can this problem be solved in n log n? To be honest, I don't know, and I haven't tried it. But I am assuming if this problem had an n log n solution, Setter might have wanted to use it as a hard problem later on rather than using it in book. Okay, so the main idea of this problem was to look at what is happening under the hood. Under the hood, only value of we are taking AL from somewhere and putting it at some another place. And if you look at it, like only the relative position of AL plus 1 to AR is changing with respect to AL. And specifically, if that value was smaller, then now you are making it an inversion. If not, you are making it not an inversion here, essentially. Like earlier, if you are taking one value, putting it at the end of something, if the starting value was initially more, then putting it at the back reduces the number of inversions we have. Alternatively, if you take the small value and put it at the end, you will get, like, take the small value from starting and put it at the back, you will end up increasing an inversion here. And essentially, this was the idea. Like, you should have probably looked at it is guaranteed that sum of n square across all the test cases is less than this. This means if you write an n square code for each test case, it will still run within the memory. Is there any other solution, like other than the brute force? Like brute force, I would say is like we are changing all the array, trying out all the L and R pair, and then computing all the inversions. So that's essentially n cube or something. May not work here. So this was problem D we had. Any questions, anyone? Why is my solution incorrect? You can probably look at the test cases which are present here. No, like I don't think the context is unrated. Like the rating change happens after 24 hours. Like I'm not sure if the greedy idea of taking element with maximum inversions may work here. Like maximum number, find the element which has more elements and less elements. Then you have to also check only the numbers which are after that number, and that might work. Like for each number, count how many numbers are more than it, how many numbers are less than it, and potentially take a difference there. No, essentially that may not also work, right? Like for example, let's look at this. Here, like the best bet is to put this 10 here, but that's essentially same for everyone, right? No, like I am thinking of the cases when you don't need to even check for the suffix there. Like for each number, you only care about a subarray where the maximum difference exists, not even the complete suffix there or prefix either. So this was problem D. Any questions, anyone? Otherwise, I will move to problem E. Akito decided to study a new powerful spell. Since it possesses immense strength, it certainly requires a lot of space and careful preparations. For this, Akito went out into the field. Let's represent the field as Cartesian coordinate system. For the spell, Akito needs to place between 0 to 500 staffs at distinct integers in the field such that there are exactly k pairs where the distance p of I comma j is equal to d of I comma j. Here it says for two integer point a and b, p of this is like the Cartesian distance, and d of something is like the Manhattan distance. And we have to ensure that only k pairs have these two values equal. Then, like, probably if we look at what does these distances mean, then let's see what does this means. Let's say this is the coordinate graph here. And let's say we have these 2 points. Like, Cartesian distance square root means like you start from here and you go directly here. And that's the distance you can get. While the Manhattan distance means you have to only go along one of the axes here, which is like this. And when can this pink line be equal to green line? Pink line can be equal to green line either when this is like this, or these are like this, pink like this and green like this. These are the only two cases when these two values can be equal, in fact. Right, when either x coordinate or y coordinate are same. That's the correct observation. If the values here are same, then this expression is just difference of x coordinate. This will also be 0, and this expression is just difference of x coordinate, and same vice versa for the other. So what we need to do over here is, let's say I have 10 points here. If I add a new point here, then the number of pairs will increase by plus 10. Because like this value will be equal to with all the values here. So what we can do over here is, in that case, if this plus 10 makes it total pairs greater than k, we just move it to the line below it. And then start everything from there. Like, the idea is, let's say if we have 10 points here, if we have 5 points here, if we have 2 points here, then we will have 10 C2 pairs, which is around 45. Here we will have 10 pairs, here we will have 1 pair. And essentially this is what we can do. Yeah, like the key is to increase y whenever we are going past k. So if I had to put in, I start with x equal to 0, y equal to 0, current line number of points on current, and total pairs, which is also 0. As long as total pairs is less than k, if I add this point on the current x-axis, then my total pairs will increase to number of points currently on the line. If this is more than k, I just move to a new line, which is y plus plus and current line equal to 0. Then I put result dot pushback, whatever my x comma y is. Then I increase x as well, and I also increase total pairs by number of points on current line, and I increase number of points from current line by 1. And essentially this ends up being the solution for this problem. And then at last print all the points you have taken here. So this was problem E. No, like the maximum point you can get is like, do we have an impossible case now? Like if we have 500 points, maximum points you can get is 500 C2 is 124750, which is more than 7 into 10 to the power 5. So we will always find an answer with 500 points. Like for example, it's not possible to get number of pairs with 1, 2, 4, 7, 4, 9. We can never get these many pairs. This value is always impossible, but like total maximum pair we can get is this, and like this is good enough distance from 10 to the power 5 to get everything. So this was the main idea for this problem. The idea was like basically if we want both the distances to be equal, either x coordinate should be same or the y coordinate should be same. So what I ended up doing was I am maintaining solutions like this. Whenever I am going past k here, then instead of putting it in the same line, I start new line from here. And if adding new point in this line no exit past k, I just put it here. And this was essentially the solution for this problem. Yes, like you can also use inverse C2. Like in fact, in the context, I also did the same. Just that instead of solving that quadrilateral, I just ran a for loop to get the value. That also works. Okay, any questions? Anyone on problem E before we jump on to problem F? The best way to prove a solution is probably to just run it all for k equal to 1 to 10 to the power 5. You will not get more than 500 points for each of them. So you can just verify it. 5 into 1e5, it will run less than a second. Like the easiest way is to just run your code for or k equal to 0 to 10 to the power 5. Okay, goodbye, banker guys. Monsters are approaching the city. To protect it, Akito must create a protective field around the city. As everyone knows, protective fields come in various levels. Akito has chosen the field of level n. To construct the field, a special is required, which is nth row of magical triangle represents a two-dimensional array. We call this array T. In the ith row, there are I integers. The single integer is in the first row is k, and let jth element of the first row is denoted by I comma j, something like this. Where A XOR B is bitwise XOR of numbers A and B. Help Akito find the integers in the ith row of infinite triangle before monsters reach this point. Let's first put it like this. Let's say I replace this XOR with the plus sign. Then does this definition looks familiar to you for like the binomial theorem here? Or like let's me search for binomial coefficient instead. Like this is binomial coefficient definition, right? For all n comma t, look at the upper row k minus 1 plus look at the upper row k value. Here we have the same thing but a XOR instead of a plus sign. And for all the boundaries, the value is 1. In this case, instead of 1, we have k here. So that should be the first intuition we have here. And now like let's probably try to form a triangle here. The idea is we have this in the first row we have k here. In the second row, first element is k, last element is k. In the third row, first element is whatever was before. First element again here would be k. Last element again here would be k. And middlemost element would be whatever is the XOR of these elements, which is 0. Then in the fourth row, we will have 4. First element would again be k. Second element would be XOR of this. This would be again k. Third element would be XOR of this. This would be again k. Last element would be same as this. Or another way to put at it is like let's count how many times XOR with k happens over here. Right here it's only once. Here it's once. Here it's once. Here XOR is once. Here XOR is happening twice. Here XOR is happening only once. Here this XOR is same as this. Here the XOR is happening 3 times in fact. Here the XOR is happening 3 times in fact. And here the XOR is happening 1 time. So the idea is instead of finding the value, let's count how many times the XOR is happening. If it's even number of times, the value is 0. If it's odd number of times, the value is k. And if you notice correctly, this is same as the binomial coefficients we have. So this was the main idea of this problem. Ith element in nth row is 0 if NCR if NCI is even, and k if NCI is odd. Any questions, anyone on this one? So this was the main crux of this problem. The question is how do we find NCR, whether it's odd or even? The idea is, 1 second. Yes, Lucas theorem is one way. I'm not sure if there is some easy way out. Like my solution definitely uses Lucas theorem. This is Lucas. This is Lucas. This is again Lucas theorem. This is Lucas theorem again. Yes, like that's the neat part. One thing you can do is like for each factorial you have, count how many powers of 2 appears. Just count number of powers of 2. So like now the number of powers of 2 in C of n comma r would be number of powers of 2 in n factorial minus number of powers of 2 in r factorial minus number of powers of 2 in n minus r factorial. And if this is greater than 0, number is even, otherwise odd. And yes, like this is a neat solution. Like as an homework exercise, like you can look at what Lucas theorem is. and that also makes this problem a bit easy. Like as an homework, just look at this Lucas theorem. But I think right now I will go and implement the solution idea. Like the maximum number we can have is up to 10 to the power 6. Let's say let's calculate it for all the numbers up to 2 to the power 6. Like the ith row in the jth column is basically n minus 1 is the factorial we have instead of n. So number of powers of 2 in this minus number of powers of 2 in I minus number of powers of 2 into t minus n. Like this can never be less than 0. If it's positive, print 0, otherwise print there. And essentially this is the solution for problem. Any questions, anyone? So this was problem F. Any questions, anyone, before we jump on to the last problem for today? Okay, moving on to the next problem. After 300 years of slime farming, Akito finally obtained the magical number n. Upon reaching the merchant, he wanted to exchange the number of gold, but the merchant gave the hero a quest. The merchant said that for the quest, the skill Rev NP would be required, which Akito by happy coincidence has recently learned. Rev NP represents the following procedure. Write the number in base P, let this be represented as this, and then revert the numbers in the base, convert m back to the decimal and return it as result. The merchant quest was to calculate the sum of this. Since the number can be quite large, only reminder x modulo 10 to the power 9 plus 7 is required. Help, the merchant also mentioned that the previous level has been calculating this sum for 300 years and had not finished it. Help him find it faster over here. It says n is up to 3 to 10 to the power 5 and there is no sum of constraint on the sum of n for the test cases here, and k is up to 10 to the power 15. So let's see what the problem statement is asking us. Let's say, how do we calculate Rev 105 in base 5? 105 in base 5 can be written as 4 into 5 to the power 2 plus 1 into 5 plus 0 into 5 to the power 0. So which this is essentially in base here is 4, 1 and 0. Now let's reverse these numbers. So basically it becomes 0, 1, 4. So what the number we need is 0 into 5 to the power 2 plus 1 into 5 to the power 1 plus 4 into 5 to the power 0. And this number is equal to 9. Reverse of 105 in base 5 is 9. So now there are multiple cases over here. If we have to find number in base n comma k, where k is more than n, is just one digit number, which is n itself. So this way for all k, for all p between n and greater than equal to k, the answer is just n. So we can just multiply this count by n and add it to our answer. So now our problem reduces to solving for k equal to 2 to n. One more thing is, like, let's look at how many one digit more than 3 digit numbers are there. One digit is done. 2 digit, I will come back to it later. Greater than equal to 3 digit. Like a number is 2 digit in this base for base r. If n is less than equal to r is less than r square but greater than equal to r, then it's 2 digit number. And if n is more than equal to r square, then it is greater than equal to 3 digits. One digit, so like the idea is to divide it into 3 cases: one digit number, 2 digit number, and greater than equal to 3 digit number. This happens when, like, the base is more than n and the value is just n, so directly calculate it. This happens only when, like, base p square is less than equal to n. So the idea is just brute force these numbers. Since n is up to 3 into 10 to the power 5, the maximum numbers you have to brute force is 3 into 10 to the power 5, square root of that, multiplied by the number of test cases we have, which is 5000. And probably, like, you can add a log factor here if you want, but this is fast enough. Like, our problem is these cases, 2 digit numbers. So the idea is, if the base is p, then the value is b1p plus b0 is equal to n, right? Here b0 is n% p, b1 is n divided by p, and the number we want to add is b0p plus b1. The idea is, instead of this, we say this is b0 is also equal to n minus p into b1. If I replace this here, My equation becomes n minus p into b1 into p plus b1. And like this is more easy to deal with rather than dealing with modulo operation here. And this equation becomes n into p minus p square b1 plus b1. Now the idea is like we can try out all the fixed values of b1. b1 equal to 1 to square root of n. Because if the number is like this, then like this b1 will always be more than square root of n but less than the value we want. So we can just try out all the fixed values of b1. We can count how many values with that fixed b1 appears, and then we can take this sum, each term of this sum. And essentially that was the solution I had. There are some nitty-gritties with respect to implementation detail, but that was the crux of this idea. Like for the range I want to find, I am maintaining numbers from all L to R. If R is more than 1, I directly count all the one digit numbers. The value will always be n, there is only one digit, and the number of one digit numbers it appears. So now my result has reduced to taking values from 2 to n. Now as long as we have more than two digits, we just keep adding numbers for all the else and we keep incrementing the left pointer here. And you can run a for loop to find all the bases, use vector or whatever ways you want to find it using the brute force way you have. Okay, now we have only the numbers between L and R, and all are two digit numbers. Here we will use this identity to find all the numbers. We will try out all the possible values of B1. We will see what all P values are there. It will always be some continuous range there. So you pick that, you find sum of P squared, sum of N into P, and sum of B1 there. So like here I generally end up using this division trick, but there are other ways to do it. The idea is you start with some left pointer L equal to R, and you try to find up to what value you can get the same value of N by I, because this is equal to B1. Now my range is, I don't really need this. And like I look at B1, then I add the same formula. N into sum of numbers from the current range I have, which is N into P. P was the base I had. Then T into all the values I had, because this is the constant factor I have. Like let me call it B1. And sum of P square multiplied by B1 subtracted from all the numbers. So B1 here, sum of squares of all the numbers from this range. This is the formula of sum first and numbers. If you want between some range, you take the difference from left and right. This is the formula of sum of n I square for some fixed range. You can take it from the range. And you keep incrementing all the values you had and you keep going. Like you don't even need this L and R. whatever you have L right now, and then you increment L to whatever value you had same up to +1, and you essentially take the minimum of R comma same F2 so that you don't jump more than L over here, and this ends up being the solution for problem G. Any questions, anyone, on any problem today before I wrap it up today? The crux was to just look at one digit number, two digit number, and all the numbers more than that, and realize that you can solve for each case fast enough using some different algorithms here. So this was problem G, and I think I'm mostly done with the stream here. Any questions, anyone, before we wrap it up for today? So explain two-digit part representation of N, B0, and P. Sure, I can do it once. Like if I have two-digit numbers, and if the base is P, then how does N in two-digit number looks like? This is by definition B1 multiplied by P plus B0. And generally we also have 0 multiplied by P square and so on. Plus 0 multiplied by P cube and so on, we don't really care about. And now if we have to reverse this number, our new number becomes B0P plus B1, right? Like this would be the representation of reverse of whatever like binary representation we have. Here the binary, this base representation is B0 comma B1. Here this base representation is B0 comma B1. The thing is we can fix values of B1 and try out different values of B1. But the problem is this is modulo, so it keeps on jumping here. So the idea is we use this equation to put in the value of B0 here. So that's why it becomes N minus B1 P, the value of B0 from the original definition of N we had, multiplied by P plus B1. Now you don't have to deal with modulo operation anywhere. It's only an equation in B1 here. Like for each fixed B1, you can try out the range of values of P you have, and you can keep doing the part here. Now if you expand it, it becomes N multiplied by base minus B1 multiplied by base square plus B1. And this B1 is essentially like N by P, B0 is N modulo P. This is hard to deal with, but this is more easier to do. Now I keep trying this value B1 from like what are the ranges of P when B1 is 1, what are the ranges of P when B1 is 2, and so on. And for each range of P, I try to find sum of P square, sum of P, and multiplied by this sum of P to the power 0, I would say. So this was problem B, and I think any questions in the chat, anyone, before we wrap it up for today? So in that case, thanks everyone for joining today. I will post this video on YouTube too immediately after I end this stream. And that's where we are. Thanks a lot everyone for joining today.